Hydrostatic pressure is a common engineering problem that affects structures like dams, floodgates and retaining walls. Engineer must know exactly where the total force acts to design safe structures that won't fail. Therefore, the objective of the experiment is to determine the center of pressure for a submerged plane surface and compare the experimental result with the theoretical value. This helps us understand how hydrostatic force works in real-world application and supports SDG 9 for safe and innovative infrastructures.
The experimental location of the center of pressure on the vertical rectangular face of the toroid from the pivot can be determined by taking moments about the pivot. So F times Y equals to W times L. So we can conclude that Y equals to W times L divided by F. The forces on the vertical rectangular face of the toroid is given by F equals to gamma HGA equals to rho G HGA, where gamma is a specific weight of water, rho is a mass density of water, G acceleration due to Earth's gravity, and A is the area of vertical rectangular face of toroid. So we can get Hg from Y2 minus D over 2, which is D is the depth. The experimental depth of the center of pressure can be derived from HPE equals to Y minus Y1. The theoretical depth of the center of pressure can be derived by the equation below. HPT equals to Hg plus Ig over AHg, where Ig is the second moment of area about an axis through the center of the vertical rectangular face of toroid, which is Vd cubed over 12. Measure the width and depth of the rectangular face of toroid.
Measure also the length from the pivot to the load hanger.
Adjust the 3-foot screws until the apparatus is balanced. This will be indicated by the spirit lever situated at the left base of the apparatus.
Using the rider, adjust the balance arm until it is level.
Using the measuring cylinder or beaker, fill the tank with water to the zero scale datum. Just touch the base of the vertical rectangular face of toroid and can be adjusted by opening or closing the outlet valve situated at the bottom of the tank.
Fill the tank with water to a certain level about 1 cm from the top line of the tank.
Place weights on the load hanger to restore the balance arm to the horizontal position.
Record the width on the load hanger and measure from the free water surface pivot to the base of the toroid.
Remove water and weight at least 9 other values and record the depth from the free water surface pivot to the base of the toroid.
Here's the example of the calculation for 0.54 kg. To calculate weight, W is equal to kilogram times 9.81 equals to 0.45 times 9.81 equals to 4.4 Newton. Next, we have Hg. Hg is the depth from the water-free surface to the center of gravity of the vertical rectangular face of the toroid submerged in water. Therefore, Hg equals to Y2, which is depth measured from the free surface water pivot to the base of the toroid minus D over 2 equals to 0.145 minus 0.10 divided by 2. And the answer is 0.104 meter. Next, we calculate the forces on the vertical rectangular face of the toroid, which given F equals to rho G HGA equals to 1000 times 9.81 times 0.104 times 0.0075 equals to 7.65 Newton. Next, the experimental location of the center of pressure on the vertical rectangular face of the toroid from the pivot can be determined by taking moments about the pivot, which F is hydrostatic thrust on the vertical rectangular face of the toroid times Y, which is the depth from the pivot to the center of pressure equals to W, which is weight, recorded on the load hanger, times L, which is length measured from the pivot to the load hanger. Then, we rearrange the equation become Y equals to WL divided by F. It's equal to 4.4 times 0.28 divided by 7.65. And we will get the answer is 0.1610 meter. Equation is IG equals to B, which is the width, times P, cube, which is the depth, and divided by 12. So, 0.075 times 0.1 cube divided by 12, and the answer is 6.25 times 10 power of negative 6 meter power of 4. In addition, the experimental depth of the center of pressure can be derived from the equation which equals to Y minus Y1. So 0.1610 minus 0.016, and the answer is 0.145 meter. Last but not least, the theoretical depth of the center of pressure can be derived by the equation below, which is HPT equals to Hg plus Ig divided by area times Hg. So it will be 0.104 plus 6.25 times 10 power of negative 6 divided by 0.0075 times 0.104, and the answer is 0.1120.
The experimental center of pressure for the fully submerged plane range from 0.1120 meter to 0.1450 meter, while the theoretical range was 0.1056 meter to 0.1120 meter. One test gives 0.1450 meter versus 0.1120 meter, about 29% difference, showing good agreement with small errors from pivot friction, depth reading and water movement. At very low depth, partially submerged results were less accurate because the submerged area was too small to balance well. This experiment used the quadrant method. Other methods are the tilting plane methods, which test angles, and the digital sensor method, which uses sensors for more precise reading. In conclusion, this experiment achieved its objective by determining the center of pressure and comparing it with theory. For fully submerged conditions, the experimental values between 0.1120 meter and 0.1450 meter match well with the theoretical range of 0.1056 meter to 0.1120 meter. This confirms the total hydrostatic force acts below the centroids as theory predicts. The results support safe hydraulic design and SDG 9 for resilient infrastructure.